All right, let's think about this here, okay? Part A, why should S of t be an increasing function?
Because they're both increasing.
What is both increasing?
Displacement.
Hang on, Ashley, what? Yeah, no matter how slow he's going, he's still moving forward. If it ever stopped increasing, if it started decreasing, what does that mean?
He's giving up.
Yeah, he's going backwards. He turned around. He's riding along. His hat blew off, so he's got to go ride back and get it. Okay, it's a movement backwards if we start decreasing, because our displacement would be getting less, so we are closer to our starting point than we were before. Okay, so as long as he doesn't turn around and go back at all, we know that it's got to be increasing.
Wait, you said that if he turned around because he dropped his hat, then it would go down?
Yeah, like here we are at 5 minutes, and our hat blew off, so we got to ride backwards, and then we got to pick up and go again.
Yeah,
So
but
wait,
on the graph, excuse me,
hang on.
Al.
I'm sorry.
On the graph,
Mm-hmm.
you said it would go down if you went backwards.
Yeah, it would look like this.
Down. What? Oh, because the displacement is on the y-axis.
Yeah, this is like home. This is home, and it's
What
like
is that?
we're
What's that?
looking from above.
Time, like 5 seconds.
Well, no, minutes. These are minutes. Think of it like we're looking at it above, and we're taking a picture of him. And here's his house, here's him. Here's his house, here's him. And then we cut them all out and we laid them side by side. His house isn't moving. Our distance, though, this is how far from home he is at this moment. This is how far from home he is at this moment. Okay?
There's a displacement on that.
Yeah. So think of it almost like, we have an aerial view here. We took a picture. Here's him, and here's where his house is. And then we took another picture. Here's him, and here's his house. And we're cutting all these little things out, and we're setting them all side by side. So we get this view of exactly how far he is from his house. Here's the total distance from his house when he stops. Okay? You can see it here in a linear look. Okay? We stop, we turn around again, and then we finally end up there. Okay, if we had gone backwards. This, it's harder to tell if he goes backwards, because what you would have is, here's t equals 5, but then here would be like a t equals 6, and then here's t equals 10. All right, so we must have gone here in 5 minutes, then a minute backwards, and then 4 minutes later we were up here again. So if it's on a line like this, a motion diagram, you really have to pay attention to those times. Okay? Now, can we find a function for Michael's speed at any time?
Yes.
What is speed? It's the rate of change, okay?
So it's a slope.
The derivative, very good. The derivative, or the slope, will give us our velocity.
What did you say that?
Okay. Why would I say absolute value of the derivative?
The speed goes in any direction.
Okay. What would s prime of t give us?
Velocity.
S prime of t is our velocity. Okay? Now, the difference between velocity and speed. Velocity is a vector quantity, right? So we have a magnitude, which is the speed, and we have a direction. How is direction indicated in our velocity? The positive and negative. Are we moving forward towards our friend's house, or are we moving backwards? Okay? So a positive velocity means we're moving to the right. Negative velocity means we're moving to the left. We'll come back to that in a little bit. Okay? His acceleration is the rate at which his speed is changing. How could we interpret s prime of t, or s double prime of t? That's going to be our acceleration. Okay? Our acceleration to the right, okay? Now, D, we could take the derivatives and plug in 15 for D. I'm not going to do that here. But at what point do we think the hill was the steepest? What do you guys think here?
Probably when you went the fastest down. It probably went like the distance was, like to cover the most distance in the shortest amount of
Just
time.
changing displacement over time.
Okay, there's an idea when we're going downhill, if the speed is the fastest there, we could be that could be the steepest part, right? Where else could the steepest part be?
Oh, upward.
Yeah, if it was steep when we were on our way there, upward. Okay, so it could be the slowest speed, or it could be the fastest speed, depending on the situation. We'd have to look. We'd have to look the closest here. Now, if we're looking at this, all right, this gets really, really flat right in here. You know, between like the what would it be? 5, 6, 7. So like between here and here, it's getting really, really flat. So that means we're hardly moving at all, right? I mean, we only covered this amount of distance, you know, in, you know, like 5 minutes worth of time almost. So we're going really, really slow. So chances are the hill is really, really steep right there. Plus, we're tired from coming all the way so far. All right? Now, going down the hill, see now we're starting to speed up a little bit. This indicates that we're now going down the hill. Okay? So the steepest part might be down the hill, but it seems to indicate from the way they're asking this that
His displacement is how far he's picking up.
yes.
And on the x-axis is the time.
Yep.
So if it just goes really far up in a short amount of time, that means he's going really slow or really
No,
fast.
really fast.
So why did you say that oh, he's going down now, so he's going really fast?
Right here, he's barely covering any distance at all
when
in a
you
long
just
period of
outlined.
time.
What you just outlined.
Yeah, here.
He's going really fast, but he's going downhill.
Yeah, here we're covering a more distance in a short period of time. That means we're going faster. Okay? So, all right, now let's get into kind of the particulars here and look at some of the details of how this works and whatnot. We already mentioned this, the displacement function. So let's talk about velocity, acceleration, and then also speed when it comes to the derivatives, okay? There are three functions that you need to be familiar with. S, V, and A, okay? S is our displacement, V is the velocity, A is the acceleration, okay? Now, if you're doing S of 0, V of 0, A of 0, those are the initial conditions, okay, or your starting conditions. Where are we when time is 0? And we start the clock, okay? Now, to get S, V, and A, S is our displacement. We find the derivative to get the velocity. And then we find the derivative of velocity to get the acceleration. That means that the acceleration is the second derivative of our displacement function, as you can see there. Now, one of the things we want to differentiate between here is our average velocity and our instantaneous velocity. Okay? Average velocity and instantaneous velocity. Okay? Now, understand, I'm not talking about average speed. talking about average velocity. So if you take a look here, our average velocity is our position at our ending time minus the position at our beginning time over the difference in time. Now, that's significant here because if I start and end in the same place, what's my average velocity? 0. Okay? It's 0. If I start and end in the same place, then S of T2 minus S of T1 is 0. So it doesn't matter how quickly I got there or how far I went in between. If I start and end at the same place, my average velocity is actually 0. Now, if we wanted average speed, that would be different, and we would have to do some other calculations. Okay? Instantaneous velocity, however, you guys could probably anticipate, is going to be used by evaluating that first derivative of your velocity. Okay? Velocity is s prime of t. You plug in the value that you want for t, and it'll tell you what your velocity is at that moment. If you take the absolute value, that'll tell you what the speed is at that moment. Okay? Now, acceleration works in a similar way. You can find your average acceleration. Okay? I already mentioned this. You can find your average acceleration by looking at the change in your velocity over the change in time. Okay? So, we could be driving 60 miles an hour. We speed up really, really, really fast to get past this car, and then we slow back down to 60 miles an hour. Our average acceleration is 0 because we started and ended at the same velocity. Okay? So, our average acceleration. Instantaneous acceleration, however, is that a of t, the second derivative of our displacement, or the derivative of our velocity, evaluated at a particular time. Okay? So, these are the concepts involved. I want to think about really understanding what these are, though. Okay? We mentioned this already. Looking at the sign of your displacement function. If it's 0, your position is at the origin. If it's positive, you're to the right of the origin. If it's negative, you're to the left of the origin. That is pretty easy to figure out, okay? And to remember. When we start looking at velocity and acceleration, though, sometimes it's hard to keep them straight, okay? The signs of v of t. You gotta, when you're thinking about velocity, you have to think of which way am I going? It doesn't matter if you're speeding up or slowing down. Which way are you actually going at that moment? That's your velocity. Okay? So, if your velocity is 0, you're not going anywhere at that moment. You're at rest. If your velocity is positive, you are moving to the right. Okay? Even if you're slowing down in your movement to your right, as long as you're still moving to the right, your velocity is positive. When your velocity is negative, you're moving to the left. Even if you're slowing down or speeding up, it doesn't matter. If you're moving to the left, your velocity is negative. Okay? So when you're thinking about v of t, your velocity, think about which way am I going? When you're talking about your acceleration, on the other hand, what you want to think about here is Which way am I trying to go? Okay? So if you're moving to the right, but you're slowing down, you're evidently trying to go to the left, right? Does that make sense? If I'm still moving to the right, but I'm slowing down, then there's a force that's trying to push me to the left. I'm trying to go that way. Huh?
Why would they see that you're stopping? If you're slowing down?
Remember, like in physics, if you throw something up, it's got the velocity when you threw it up, and gravity's pulling it down the whole
Yeah.
time. So it goes up for a while, getting slower, slower. It's being pulled down.
So there is a moment when you come to a stop, but then assuming that everything continues, that acceleration continues, you'll start moving in the negative direction. Okay? So it's kind of like, you know, these floors are kind of slippery. If I ran that direction and then tried to change direction real quick, I would slide a little bit before I actually started coming back this way. Okay? That moment when we're kind of sliding is when our acceleration has now changed directions, but our velocity hasn't quite caught up to it yet. Okay?
I thought velocity was the change in direction.
Velocity tells us which direction we're going. Okay? And when velocity changes from negative to positive, that's when the actual change of direction takes place. But before you can change direction, it's like you have to decide you're going to change direction. Okay? And you've got to stop that momentum going this way so you can start coming back this way. That's when the acceleration changes sign before the velocity will change sign. Okay? So that's kind of the idea with the acceleration. So if your velocity is increasing, you're getting more positive. Even if the velocity is still negative. If it was at negative 12 and now it's at negative 10, you're getting more positive, so that's a positive acceleration. Okay? If your velocity is decreasing, that means you're getting towards the negative, all right? So if your velocity was 12 and now it's 10, you're getting towards the negative, so that's a negative acceleration, okay? If you're at negative 5 and you get down to negative 7, you still have a negative acceleration. It's pushing you further towards the negative, further to the left, okay? Now, understanding these two together are really how we determine, are we speeding up or are we slowing down? Okay? And you got to think about, are my velocity and acceleration working together or are they working against one another? Okay? Think about it. If my velocity is going one way and my acceleration is going the same way, what's that going to do to my speed? It's going to make it faster, okay? If I'm going this way and then I'm getting pushed even faster that same direction, I'm going to go even faster in that direction, no matter which direction it is, okay? If, however, my momentum is taking me this way, but I'm trying to go this way, that's going to slow me down, okay? So that's where this comes in here. If the signs of V of t and A of t are the same, and notice both positive or both negative, then the speed of P is increasing. Okay? We're going to be getting faster. If velocity and acceleration share the same signs. Okay? So guys, when you do your sign diagrams, all right? Let's say that, here's our velocity, and, you've got some critical values, okay? So let's say it's negative here, positive here, and negative here, and then you do a sign diagram for acceleration. okay? And let's say that you've got, a positive here and then a negative here. Check this out. I could kind of split this into segments and identify, okay, here's a negative velocity but a positive acceleration. I'm going to be slowing down, right? However, here's a positive acceleration and a positive velocity. That means I'm going to be going faster. Okay? Here I have a negative acceleration and a positive velocity, so I'm going to be slowing down again. But then here I have a negative with the negative, so I'm going to be going faster again. All right, does that make sense? So, anytime they're working together, both signs are the same, you're going to go faster. Anytime the signs are opposite, then the speed is going to decrease. We're going to go slower. All right, because those are working against each other. Okay? Now, let's take one of these kind of all the way through.
Good afternoon, North Broward students and faculty. This is Ryan Matamoras from the men's varsity soccer team. Today, I invite you to support our varsity soccer team at 7 p.m. against Benjamin High School in Jupiter. Thank you in advance for the support, and we will do our best to bring the trophy home on Friday. Vamos! Thank you.
All right. Okay, so part A says we want to find expressions for the particles' velocity and acceleration and draw sign diagrams for each of them. Okay? Now that doesn't seem like that much of a problem, but that's where most of the work here is going to come from. Okay? We have S of t. I'm going to write this down here so I can see it. S of t, t cubed minus 3t plus 1. Okay? So, I want velocity. Velocity is s prime. Okay? What's the expression? What's the expression here for velocity? Good. 3t squared minus 3. Okay? Then I want acceleration. This is s double prime. Good. So this is 6t. Okay? Yes?
It's always s prime, and acceleration is always s double prime.
Yep. Now, it says to do sign diagrams. To do sign diagrams, first of all, we need to find what?
Critical values.
Critical values for the v of t, and then also find out where a of t equals 0. Okay? So, here's our number line. Can you tell just by looking here what values of t are going to give me 0? 1 or? Negative 1. Okay? So 1 and negative 1 are going to give me, are my critical values. Okay? The sign diagram for acceleration, where am I going to equal 0? At 0. Okay? Now notice here I drew these parallel to each other because I want to see what we just looked at in our hypothetical previously. Okay? So let's actually do the sign diagram here. Since I've got green, for acceleration, to the left of 0, our acceleration is negative. And to the right of 0, it's positive. Okay? So before I get to 0, I want to go to the left. After I cross past 0, I want to go to the right. Okay?
Wait, the 3t squared minus 3 is weird because if you do like a negative 1, then it's not But like negative like 9 than it is.
Well,
Squaring takes this away.
-1 was a critical value, so it'll equal 0, right?
Yes, so I'm saying like you're trying to look for numbers -1, like lower than 1. So like if you do -2,
Mm-hmm.
then
It'd be 3 times +4 minus 3, which would be a positive, right? So I know that I'm going to be moving to the right until I hit -1. Then, if I plug in, say, a 0,
-3.
it'll be negative, so I'm moving to the left. And then once I get past 1,
Still positive.
it's positive, so I'm moving to the right. Okay? Now, I'm going to skip right here, F. Okay? F. What time interval is the particle's speed increasing?
Greater than 0. It's not fixed.
Speed. For speed to be increasing, what has to be true?
It's greater than 1.
Let's think this through. In order for speed to increase, what has to be true? Same sign for acceleration and velocity. So right here, I'm going to kind of separate these like this. Okay? So I have a positive and a negative. I have a negative and a negative. I have a negative and a positive. And I have a positive and a positive. Now, notice up here they said,
Please for this introduction, will Michaela McCullough-Pelly please report to the middle school office? Michaela McCullough-Pelly, please report to the middle school office.
all right. So now one thing to understand here is even though we have this function and these values, we're starting the time when t equals 0. So we're actually going to ignore everything to the left
Why would you do that?
because we're looking at it from time equals 0 to time equals 2. Okay? So we're just boxing in from 0 over here to where to 2.
Why don't we even do the whole? Oh, sorry. We didn't need to, right? Do that. I didn't need to.
You didn't have to, but it's nice. Okay? So in the interval from 0 to 2, when are we speeding up? From 1 to 2. Okay? From 1 to 2. Okay? From 1 to 2, we're speeding up. And we're actually speeding up as we're moving to the right.
From 0 to 1, you're in Z. You're going down.
From 0 to 1, we're actually moving to the left still, but we're trying to move to the right. The acceleration is positive, but the velocity is still negative. So it's like we're sliding to the left, trying to go to the right, and finally at 1, we're able to change directions. Okay? Now, the initial conditions. The initial conditions. What are the initial conditions? Where are we? First of all. Where are we when t is 0?
We're not moving. 0.
1.
We're at 1. We're at that spot, 1. Okay? So s of 0 is 1. What's our velocity?
-3.
-3. So at that moment, we're actually moving to the left, right? We start moving to the left. And then our acceleration at that moment
0.
is 0.
That took
So you
0.
didn't put
Okay.
A 0.
Huh?
You didn't put A 0.
Yeah, that's okay. Now, find the position of the particle when changes in direction occur. When will the change in direction occur?
At 1. When it goes from negative to positive.
When what goes from negative to positive?
The position?
No. We're talking about change in direction. What determines our direction?
Velocity.
The velocity. So when the velocity changes from negative to positive, so that happens right here at 1.
Wow.
Okay? Now that's a time equal to 1. Okay? So that's time equals 1. Where are we?
Negative 1.
Okay? We found at 0, or at time 0, we're at 1. Okay? So that point when time is 0.
Oh, no, we're at 0.
Now we're finding at 1.
We're at 0.
Come on, guys. When time is 1, where are we?
0.
Negative 1. Okay? We're at negative 1 when time is 1. Okay? So the first leg of our trip is this right here. Okay? Then at time 2, plug in 2, 8 minus 6 plus 1, we're all the way over here at 3.
That was pretty fast.
So there was a change in direction. Yes. And we're going fast because now our acceleration and our velocity are working together to push us this way right here. Okay? All right.